Okay, in this video we're going to talk about gravitational fields. Now the next couple of videos are going to be talking a lot about fields in their various forms. Gravitational starting off with, then electric, then magnetic, and you'll see those videos come on the channel very shortly. But let's jump straight into it. So gravitational fields. In order to understand gravitational fields, we need to understand Newton's law of gravitation. Now Newton's law of gravitation effectively suggests that there is a force of attraction between two bodies of mass, and they attract each other, and the force of that attraction is directly proportional to the product of the masses. So we're saying that the force is directly proportional to the product of those two masses. It's also proportional to the 1 over the distance between them squared. That distance there. We call that distance r. And that's from effectively a centre point, not from the surfaces, because especially when we start dealing with planets and things like that, you need to be aware that we're not dealing with the surface of these objects, we're dealing with the centre point masses of these. And effectively, from these two relationships, so the effect is inversely proportional to r squared, and it's proportional to the product of the masses, we can create Newton's law of gravitation. And Newton's law of gravitation is this equation here. Now, as you can see, there's a term I've thrown into this equation that you've not seen yet, or I've not suggested any yet. This is the gravitational constant. Okay, gravitational constant. And it will be found on your data sheet, and it has a value of 6.67 times 10 to the minus 11. Okay, it does have a unit. That unit is, if I remember off the top of my head, meters cubed, kilograms to the minus 1, seconds to the minus 2. So that's the units for that. It's not hugely important that you remember the units at this stage, but it is important that this is a number, the capital letter G. Don't get it confused with little g 9.81, the accepted force acceleration due to gravity. So here we are, we have Newton's law of gravitation, and that there is a force of attraction between these two bodies which is directly proportional to the product of the masses and inversely proportional to the square of the distance between their points of those masses. And this happens because of a gravitational field. Now each of these masses has a gravitational field which effectively exerts a force on something in that field. So far you will have understood that we have and we utilize gravitational fields when we look at things falling to Earth. And say we have an object of mass in that, so here's Earth. So we have an object of mass in this field, and these field lines show the direction of motion that object or ball or mass will drop when released. And that acceleration is due to that force of attraction between the mass that is the Earth and the mass of that object. So you could even suggest that the Earth is falling towards this little mass. It's not very viewable, and it's not sensible to say that because of the sheer difference in the mass. However, that is technically the case. They exert equal and opposite forces on each other. So, when we're looking at these forces, this is what brings about the acceleration due to gravity, g, that you hopefully well know is 9.81 meters per second, the acceleration due to gravity. Now, that is actually not so much an acceleration anymore, it's now a field strength. It's the strength of this field. It's the amount of speed that this object is going to gain per second when placed at this point in this field. And so as a result, what we can say is that this is not so much an acceleration anymore, but a field strength. Which is a very, very nice way of putting it. And oftentimes we represent a field strength by rearranging Newton's second law, F equals ma, to A equals F over m, which effectively says it's an amount of newtons per kilogram. So now this field strength is now not 9.81 meters per second, it is newtons, sorry, I'll do the correct terms, newtons per kilogram. And that is saying that what we've got here is when I put a mass in this field, I have a certain amount of force acting on it per unit mass. And as a result, that leads to an acceleration. This is what we like to call a uniform field. It's a uniform field because you'll notice that I've drawn this on purpose. The spacings between these lines is effectively the same. And this is a really nice way diagrammatically of showing that there is a constant field strength. And we appreciate that because we say close to the surface of the Earth that the field strength is 9.81 because for all intents and purposes it is uniform. However, in reality, this is a bit of a fudge because the Earth is not flat. This field is technically not uniform. It will spread out and it will get weaker. So let's have a look at what's actually going on for the Earth. So here's the Earth. And as will be suggested, we've still got those gravitational field lines heading towards the Earth. They're heading towards the Earth because they're indicating which direction a mass would travel in this case. So if I put an object here, then we would expect it to fall to Earth. And so what we're going to look at here in a second is we're going to see, well, what is the difference between that previous uniform field and now this, which we call a radial field. And the radial field we can see here is different because what do you see about this distance as opposed to this one? Well, hopefully you can see that this is much smaller than this one. And it's actually getting wider and wider and wider. And that tells us something about the field strength. It tells us that the strength is getting weaker as we move away from the object. Because the spacing of those field lines is getting more and more spread out. This is a radial field. Now, it's the interaction of these fields and the field lines which creates that force, Newton's law of gravitation's force, which allows those masses to be attracted to each other. Now, we've already suggested that for a uniform field, we accept the field strength to be 9.81. That's close to the surface of the Earth, newtons per kilogram. But what about at a position much further away than the surface of the Earth? What about this position right here? I'm going to draw this over here so it's easier for you to see. So what about a position here at a distance So it's no longer part of the uniform field that we accept on the surface of the Earth. It's much, much further away. So the value is no longer going to be 9.81. It's going to be something much less. Well, how can we work that out? Well, we can then utilize Newton's law of gravitation to help us out a little bit. F is equal to gmm over r squared. Now what we can do is we can do a little bit of fancy rearrangement here, because as I said before, over here, I said that the acceleration due to gravity was force over a mass, otherwise known as the field strength, G, 9.81 in a uniform field. Well, this value of G is now going to change because I'm at a much greater distance. Let's see how much it changes by. So if we rearrange this equation slightly, I can get F over m equals G m over r squared. And it's actually quite nice now that we can spend a moment just looking at what values we're talking about here. This is the capital M. This big M right here is the Earth. It's the thing that's creating the gravitational field that we want to know about. We want to know what the gravitational field strength is there. This little m is the mass at that point. Notice what we've got over here. We've got F over m, F over m. This is the field strength. This is an equation for the field strength. So we can say that the force due to gravity is now going to be G m over r squared. And what's the real variable here? Well, the real variable is the distance. And notice how it changes. It changes inversely proportional to r squared. So we can say that the field strength is inversely proportional to r squared, or proportional to 1 over r squared. And that is what we like to call the inverse square law, which explains why the field strength gets more and more weaker as we get further and further away from the center of mass of the Earth. So we'll leave it there for now, and in the subsequent videos we'll start looking at how we can develop this further to look at things like Kepler's laws and then eventually apply these same kind of ideas to electric fields as well.